Hi, everybody. My name is Jared Longfox. I'm a planetary exploration research scientist at the University of Central Florida and Brown University. Today, at the AIAA Space Resources webinar series, this event that you're at focused on education and outreach for anyone from professionals in our community to K-12 educators and K-12 students. To become more acquainted with the field of space exploration and space resource utilization. It is all tied, after all. And today, we're fortunate enough to have Dr. Jacob Yates with us. Today, Jacob is going to talk to us about his hypervelocity impact testing into advanced lunar simulants to and modeling of the damage to surface materials, as well as inform us on the gardening processes that shape the surficial regolith. He'll talk to us about some of his upcoming ESA/ASI Lumio CubeSat mission work. That's going to give us a really cool look into how the micrometeoroid flux on the moon is, and the hazards that future miners and habitats must withstand. And by understanding that hazard, that'll allow us to learn a lot more about how to characterize and mitigate the risks, saving people and equipment, lives, time, and money. So I'll turn it over to Jacob here. I'm going to go off video to save some bandwidth, but I will be here. I will. Oh, I forgot to mention attendees. I know I don't think you have a chat function here, but if you need anything, there should be a Q&A button, like a little speech bubble with a question mark on it on your bottom little ribbon in your Zoom window. You can click that and punch questions in as we go, and we'll take them as at the end of the presentation when Jacob's done. So be thinking about what you want to ask, and we can go from there. I'll be here if you guys need anything. But for now, Jacob, the show is yours. Thank you for taking the time.
Thank you, Jared. I'll do a quick comm check. I assume you can hear me loud and clear.
I
And if you
can.
Perfect, perfect. Well, thanks again, Jared, for that lovely introduction. Good morning to most of you. Good afternoon for those who are on the East Coast. I want to try and hit all time zones for the continental United States. And for anyone around the world, salutations. Thanks for coming. Yeah, I'm going to jump right into it. I'll start sharing my screen.
Looks
All
great on
right.
my end.
Okay, great. Yeah, so as Jared so eloquently pointed out, the goal for today's talk is to talk about if we're going to build habitats on the moon or any planetary body, you need to characterize and quantify and understand what those hazards are so you can mitigate that. And one of the challenges that researchers have had is how are we characterizing uh, the hazard environment, at least as it pertains to micrometeorites and their subsequent ejecta. Many studies, for those who have been wondering, many studies have been done on radiation, on the thermal aspects. I won't be covering those. Mine will be specifically focused on the ejecta and micrometeorite and meteorite hazard that it poses. Uh, and I think it'll shed some light on some of the challenges that we face that then impact, pun intended, what the modelers have to actually come up with to develop a risk mitigation plan. What materials would they need to use in the future? We've had 30 years of ISS, as well as other activities in low Earth orbit, both by the United States, by Russia, and the European Space Agency. But those were in a low Earth orbit. We're going back to the moon after 50 years, which is fantastic. But now it's not a camping trip anymore. Now it's going to be long term. So we need to start thinking in those long term effects how that's going to be. So that's what the purpose of this talk is going to be about. And I'm the PI for the ARMOR program. That's the Advanced Research in Moon Operations Resiliency. And I'll talk about that a little bit more at the end. So make sure the advance works. We'll talk about the hazards of why we're here. So we're now part of the Artemis generation. When I was younger, much younger, I heard from folks about the Apollo, and it sounded exciting, and I was always very envious. But now we're here for Artemis, and if all goes well, next month we'll have a launch of four astronauts as they transit out to the cislunar space, do an orbit, and come on back and see us here on Earth. And it's exciting. And that's Artemis 2. And that's going to lead to Artemis 3, which will be a landing. And then Artemis 4 and beyond are those long-term habitation that's going to occur. It'll probably start off a couple weeks on the surface, going out to maybe 30 days, and then longer as you start looking in those timelines. And I have down here in the bottom center of the chart, that's the South Pole. That's the area of interest that NASA, as well as other groups, both China and Russia, and commercial ventures are interested in. I'm not going to get into this in detail, but there is water resources and other advantages that one can go there. And so we're going to set up there. What's our micrometeorite impact going to be for those future explorers and miners there? Both in terms of large meteorites that we're used to seeing here on the Earth when you pick something up, or at the micrometeorite level. Remember, there's no stratified atmosphere weeding those out from coming down. Those are going to start to impact the surface that we'll need to consider. And then likewise, we're going to talk about the ejecta that comes from that. Remember, no atmosphere, no appreciable atmosphere. There's an exosphere on the moon, but no appreciable atmosphere to really slow particulates from zipping across uh, laterally the surface of the moon for nearby astronauts if they're working down there. So, long-term missions on the surface. What's our risk assessment for people, habitats, and vehicles? That's what's going to be on the surface. And what can we operate through on? A lot of times, the military or even satellite operators, they have this ConOps concept of operations of, okay, if detrimental effects occur, can you operate through? Uh, it's raining here in Southern California. I know, which is rare, but a normal ConOp for a regular person would be, okay, I'm going to throw on a rain jacket, and we've had 60, 70-mile-per-hour winds. Maybe need to batten down the hatches if you have outdoor furniture. That's operating through. Uh, for satellites, they may need to go in safe mode, or can they operate through and have a few hits? That's one thing if it's a satellite zipping around low Earth orbit. It's very different when you're on a planetary surface. We're going to get into that. So, meteorite ejecta, there was that classic view of the moon that we see craters, and that happened millions, if not billions, of years ago. But I want to showcase something that happened on March 17th, 2013. Uh, I like this particular one. There's been others subsequent this, but this particular one was well documented. We saw not only the lunar impact flash occur from ground-based observations here in the United States, but the Lunar Reconnaissance Orbiter was able to capture not only that impact that you see in the lower left hand of the screen and the ejecta, but on the right-hand side, you see a bunch of spalations, secondary effects, the ejecta going out up to 32 kilometers away. That is much larger surface area than any planetary geologist or modeler thought of that can occur in today's lunar environment. We've always known that has occurred in the Copernican period, that's the last 1 billion years, and we used to think those were on the orders of hundreds of thousands, if not millions of years time scale. Well, this occurred in 2013. There was another one in 2017. And this is just under one orbiter where you could see a large lateral ejecta displacement occurring. So we had to rethink how much ejecta can pose as a hazard. And so that's where the genesis of this project got started. So we wanted to know, how is it damaging to habitats, spacesuits, and equipment, this meteorite ejecta when they're traveling at hypervelocity speeds? And fundamentally, remember when I mentioned about the modeling, do we understand all the parameters associated with these risks? There have been classic studies here on the Earth since the 1960s. I know at NASA Ames and White Sands Missile Range about hypervelocity test, having small aluminum pellets hitting uh, aluminum plates or steel plates and iron plates and lead plates to seeing how well they do. However, those were looking for, short term, an astronaut goes out in space. If an impact occurs, what happens? But what's that long term detrimental effect? I'm going to get into what some of those modeling parameters that we need to understand. And then at the bottom is for modeling, can we effectively block or degrade the lunar meteorite ejecta for future ops? Is there a sequence of shielding that's being done? And I'll get into that a little bit later on the type of shielding that, okay, maybe some impacts do occur, but can we still operate through in a safe environment? So lunar impact flashes, I mentioned that earlier. What is that? That's actually in the top of the right-hand screen. You see this light curve. Then above, it was an impact that occurred, and it lasted all of 1 second. The impact, when it strikes the surface, it actually sends up a plume of material, and it gets super hot. And that ejecta, that glow, that residual glow, is what we see and telescopic observation. And this from a ground-based observation. And the Yanagasawa team, they were able to quantify that light curve. It's rare for us to quantify a lot of light curves because most of them last only 10 to 60 microseconds. So at best, that's maybe like 1 or 2 pixels on a fast CCD that's on digital video that you have. Um, so this was one of the larger ones that we were able to quantify and able to see that the impact melt, that high temperature vapor is getting spread, it's getting dispersed radially, asymmetrically away from that site. So we learned very quickly early on, it's not a uniform cone as it spreads apart, or I'm sorry, hemisphere that spreads apart. It's very asymmetrical in that process. And then we also have a problem in monitoring because remember I said ground-based telescopes. Well, ground-based telescopes are subject to what other astronomers face, and that is, you have weather effects, you have satellites flying over, you have cosmic ray hits on the CCD. So a lot of times you need to have two telescopes that are more than 20 kilometers away observing the same phenomena. So our understanding, and that's all to say, our understanding is limited by our flux rate because we know we're not getting all of the impacts that are occurring. And remember, these impacts are only on the near side hemisphere when we see these events. And by the way, before I forget, because I know I don't have that slide on here, the the impacts that we observe with ground-based telescopes are only on the dark side. That is, when you see the moon at like quarter moon or crescent moon, that unlit side, but we see it because of planet shine. That's the sunlight bouncing off the Earth and reflecting, and we see kind of that dark lit part of the moon. That's where our telescopes are observing. So during a full moon or where the moon is bright, we cannot observe those lunar impact flashes on the bright side. So we're limited by understanding just how much impacts are occurring on the surface of the moon. And we'll come to that later in the talk on how we might be able to mitigate that. So I know I threw some terms out there, so I'm not going to go through this whole slide, but I'll just summarize that many folks are familiar with hypersonics. We hear about that with the Space Development Agency. They're doing all sorts of hypersonic testing and understanding. I'm talking about hypervelocity. A hypersonic means that you have something moving fast, very fast at Mach speeds through a stratified atmosphere. In this case, I'm using the classic U.S. Army definition of any projectile that's traveling more than 1 kilometer per second. And that has different type of effects than, say, like ballistic, for those who are familiar with small arms weapons or guns. Those have different physical effects for that. And a lot of times when I'm talking about hypervelocity shots in the future, in this brief, I'm going to be mentioning ones that are near lunar escape velocity because that's going to be your upper threshold of ejecta that'll be traveling at high speeds. If it gets beyond lunar escape velocity, well, then we don't have to worry about it anymore. It's going to get blasted off the surface and come back either orbiting around the moon or sometimes coming around back to Earth. And we do have lunar meteorites in our collections indicating that. So most of the hypervelocity experiments I'm going to show are around 2.4 kilometers per second. And then on the lower right, these are some of the graphics that came back from the LDIF, that's the long duration exposure facility that was left up in low Earth orbit for 5 years. And we were able to observe, and then brought back down by the space shuttle. Then we were able to observe those micrometeorite impacts on the actual LDIF facility. So back to the risk. Probably the most important aspect is trying to characterize what our risk is, but also understanding what our gaps are. So remember, I mentioned previously, we don't have an accurate flux rate for the moon. We have estimates based on terrestrial, but again, those are estimates based on terrestrial observations. And remember, those terrestrial observations, the stratified atmosphere does act as a filtering mechanism for our lower echelon meteorites that are coming into the surface of the planet, our planet. And then you have dispersal patterns. Remember, I said when these things are hitting, they're hitting, and the ejecta that comes out is asymmetrically. So how do we quantify those distal ejecta that's leaving that crater from far away? And now your particle size. We have made some assumptions on common ejecta types, but is that in the normal Gaussian distribution curve? We know that they're in some of them. Do we know if it's all of them? That we don't know about yet. Um, and then what's our prioritized list of materials that we're going to use for the future? We have a list from NASA Marshall Space Flight Center of proposed materials that we'll use for Artemis 4, but that's not including mining equipment. That's just for astronauts to go there, do some exploration, pick up some rocks, look for some water ice. But those long-term mining effects, that's going to be a little bit different. And I'm sure if I was in your shoes, I'd be asking, well, give me an example of what that is. Well, if you go to Home Depot or Lowe's or your favorite handyman store and you buy a hammer, that's a stainless steel hammer. Well, when you get below sub-freezing levels on the surface of the moon, that hammer will shatter into many, many pieces. So you'll actually need to get a nickel hammer because a nickel hammer will actually be able to withstand those drops in temperature. That's just one example that future miners will have to readjust of the type of materials that they'll need to operate in the lunar environment. And then at the end of the gaps I mentioned, what's the operate through by mission planners? Obviously, the idealized one as a taxpayer and as a fan of the astronaut program. Well, I want these astronauts to survive. I don't want them to be in a severe setting. But many times on the Earth, we have people when they work, we realize, okay, there's a thunderstorm, rainstorm. It's fine. Oh, lightning hit. Now let's bring the workers inside now because it's dangerous. We have a long-term understanding of what risks are here on the Earth, but we don't quite have that yet for the moon. And so we need to work through what that operate through is for mission planners. And then characterizing the risk, I used the equation that most of us are familiar with in our Physics 101 class. That's the kinetic energy equation. That's where we used mass of the particulate. This will be the bolide that I'm going to use for the hypervelocity experiment, and then the measured velocities to get our kinetic energies out. And one thing I forgot to mention in the previous slide, let's see if I can go back. Um, a a bullet or projectile for a gun traveling, and most guns on the average are 500 to 750 meters per second. Uh, that'll do about that'll do some damage. And I want to actually, I just realized I'm getting ahead of myself. That'll do a certain amount of damage. And at the hypervelocity, it's a greater damage. And we're going to get into that a little bit later. So forgive me for going back. I realized I was trumping my own or stepping on my own message. So research methodology, what did we do? So we went to a two-stage light gas gun that was at the Hypervelocity Impact Lab at Texas A&M University. They are part of the University Consortium of Applied Hypersonics and the University of North Dakota, which I was a member of, and Texas A&M University are members of the UCA organization. And I was able to get some time on their hypervelocity impact lab where we used their two-stage light gas gun in the April and October timeframe. The particular projectiles I used were 4 millimeter aluminum beads to represent the iron lithic fragments. So if an iron meteorite is going to strike the surface, we always say, hey, the meteorite got vaporized. Well, that's kind of true. If it's a stony meteorite, it tends to get vaporized, but residual particulates are out there. But when it gets blown apart, it's really hard to locate those original stony meteorite fragments. On the other hand, an iron meteorite, when it strikes, it does get blasted apart, but those iron lithic fragments do fly across the lunar surface. So we thought that was probably one of the more dangerous ones. So we used a 4 millimeter aluminum bead to mimic that density of the iron lithic fragment. And then we also chose a 8 millimeter glass bead to represent crystalline lunar spherules. Those who have been following the Chinese landing missions, they have found these glass beads on the surface. Some people think it was like a new discovery. It's actually an old discovery. The Apollo 16 astronauts found this when they were in the lunar highlands. And what's believed to happen is when you have a meteorite hitting the highland material, which is made out of anorthosite. My apologies for this quick geology lecture, but when it hits anorthosite and it vaporizes that rock, it forms these glass spherules that blast off the surface. And because there's no atmosphere or anything else, it forms a sphere. Do we have something similar here on the Earth? Not quite, but we do have something vaguely similar. And I know I'll get in trouble with a few of the meteorite people when I make this analogy. But for those who are familiar with tektites, tektites are small, um, if you want to think of like obsidian in terms of a dark color, but they're nice, smooth, and rounded. And these tektites are found near impact craters. I know they've been found around Meteor Crater in Arizona, as well as places in Southeast Asia. They've been finding in a tektite field. However, those are formed in a kind of aerodynamic shape and because of the atmosphere when it passes through. But remember, there's no atmosphere around the moon, so they just form these crystalline lunar spherules, these nice glass beads that are found. And because of their propensity of being found, we decided we should use a CLS representative. So we found 8 millimeter glass beads and these became our two end-member test sites that we used. The projectiles rode in a sabot, and we got them up to an optimal speed of around 2.2 kilometers per second. Reason why 2.2 and not 2.4 is because the two-stage light gas gun, while it's very accurate, there is a little bit of variance depending on how much gunpowder you use, and that variance is around 200 meters per second. So we wanted to make sure we didn't exceed 2.4 km in that process. So that was our testing procedure. And then we did an assessments on what was the depth of penetration, or was there a puncture, or was it flat out disintegrated? So I kind of mentioned the lunar highlands in the upper left-hand side. I'll see if you can see my cursor. So most of the astronauts landed in these dark places called Maria, and I said that the Apollo 16 one landed in the bright areas. That's the lunar highlands. And so we took lunar highland simulant from back then Exolith, now Space Resources Technology, that graciously helped us out with this. They provided, I want to say a couple hundred kilograms of lunar highland simulant that we used for our testing material. And we ran through a very series of experiments. And the lower right is our two-stage light gas gun. Um, it's roughly 13 to 15 meters. I know that says 13.7. That was when it was first set up, but we have some additional equipment that's around it. So when you walk around the whole thing, it's almost at 15 meters. And basically on the far left, I'm sorry, the far right, you start your sabot, you fire the first stage. it hits your sabot, which then has the target material inside, pushes it all the way to your blast tank. The blast tank then separates your sabot, and then the projectile punches through to the end to your target tank. And I'll show a little bit more detail of that. On the left-hand side, here's our time series step. You see the trajectory of the projectile. It comes through. It's going to hit. This is where the regolith is lined up in the first frame. And then the next frame, this is where you see it punctures and it forms our ejecta plume at this point. And this material here was the acetate that was holding in the regolith from spilling out. So that was how we ran these tests. And this is kind of a close-up of what we're showing and how we measured the velocity. This is kind of the key critical part. We have two laser range gates. So when your projectile comes through on the first one, it starts the timer, hits the second one. That's how we glean our velocity in the process. Special thanks to Dr. Tom Lacey and now Dr. Jacob Rogers, as well as Sid Davis, our lead gunners, in enabling this to happen. And then how do we record it? Well, we have a special high-speed camera doing 1 million frames a second, and then we have the lighting doing more of a backlight to it. When you shine on the front light, you see the particle go through, but that ejecta gets washed out on the light. So we created what's called a shadow graph. So you may not see the particle up close per se, but that it post-ejecta debris and effects comes across brilliantly. And so this is why we have special lighting conditions when we see that. And this Joker is the one that you see on your screen. This is where this is the business end of the two-stage light gas gun where you shoot it down. This is preparing the materials. This I'll actually talk about in one of the upcoming slides. It might be the next one or the third or the second one from now. This is the polyurethane garment. So when you think of astronauts and their liquid-cooled garments, this is the material. I'm doing the measurements ahead of time to make sure it's ready. Here's our regolith bucket, putting this in. This is where we packed it in. We did vibration and compaction to mimic what's on the lunar surface. So it wasn't all loose and unconsolidated because over eons of geological bombardment, that lunar regolith soil, while the top part is, loose, the rest of it is pretty compact in there. And then here's our sabot that pushes the material down. Um, and then actually, I'm sorry. So, and then here's our two projectiles that are the sabots. This is the pusher, the kind of the plunger pusher that pushes them down. And on the left-hand side is our 4 mm aluminum projectile representing the iron lithic fragments. And then on the right side next to it is our glass bead that we have there. And oh, and then here's our target tank that you see. It's in the back end. This is when you pull it out. You mount your target material here. In this section is where our lighting system is. This is the brackets where we do our holding. Down here, you see one of the test targets, and then you see the multiple steel plates that act as a Whipple shield in case if something blasts through. These got to stop it because you don't want to blast the back end of the tank. It's rather expensive. And these are your steel plates that make sure nothing can go past. And I think when they got close to 9 kilometers per second, they did get the back one, but most of the time they really never get above 6 kilometers per second. So I know this talk is on space resources technology, so let me get to the meat and potatoes, which I'm sure some of you are probably interested in, and that was, what did we test? So we got the list of various materials that Blue Origin, SpaceX, the Orion program, and other spacecraft have talked about using. Aerogel has been used as a protection for certain electrical components. Aluminosilicate is an optical screen that astronauts and others plan to use touch screens. And so we grabbed one of those Gorilla Glass plates. And then we grabbed the EVA suit layer that I mentioned. Graphene has been used for some of the electronic protection. And then our regolith simulant. And then we had one team that put together the regolith and used their own epoxy to be a reinforcing material. And then we had a thermal tile, and the thermal tile was from the space shuttle. And granted, we're not going to land the space shuttle, but there is similar thermal tiles that are going to be used for upcoming CLIPS landers. Actually, I think one has already been used. And I know some subsequent landers that have talked about being resupplied for cargo or other materials are using this similar type of tile, this type of tile material in this process. And then people have talked about inflatables. So we use the Spectra fabric that's been used in several inflatables in the past and upcoming in the future. It's on a comprehensive list, but we thought it was a very good diverse list since many have talked about using these materials in the future. And I'm going to call out the regolith ones shortly. So we kind of saw this graph before, and again, we're looking for if it was successful, it stopped it, and if it did, what was the depth of penetration, or did it puncture through, or did it disintegrate it outright? And then these are the results from each shot. Here is the polyurethane garment from the EVA suit. We had two puncture holes using the iron lithic beads. I don't expect everyone to read this part, but you could see the impact from the side, and this is the ejecta as it comes out, and your plume ejecta to the right as it follows the trajectory of uh, uh, the 4 millimeter projectile. And hopefully this will play. So I'm going to go back and play that one more time and kind of do a little bit of stops just to kind of show what you're seeing in here. Oop, let's see if I can pause it. There we go. So that bright flash you saw is that thermal signature. That's the signature you're seeing with those lunar impact flashes that superheats the vapor in the process. You'll see a little bit of ejecta coming out here, and then your plume ejecta. Excuse me. When you think of that plume ejecta, if you're in a habitat or in a rover or in an EVA suit, that second order of shrapnel or debris is coming in with that area, with that. So that's something that we need to keep an eye on. So here's a test that we did with an 8 millimeter glass bead, uh, and it hit the surface, but but it stopped it as well. And let me show what that looks like. So you could see the flash, and it basically disintegrated inside the material. There was no glass left over. Basically, got superheated and got blasted off in the process. So this epoxy did extremely well. The interesting part of this epoxy using the Lunar Highland simulant is it not only created a impact on the front, but it also created an antipodal crater on the back, which was interesting to see that. So while it did stop that, that shock wave did reverberate through the other side. So I want to get into with the time remaining of those other characteristics that we're trying to understand, and that is the flux rate. So the European Space Agency and the Italian Space Agency have proposed a small sat to fly out to the lunar moon, Earth moon 2 point in a halo orbit. The idea is it'll transit out for several months to get in the optimal L2 environment and then form a halo environment. And the reason why it's going to do a halo so it can maintain consistent line of sight with the Earth. But in this halo orbit, it will also see that far side hemisphere, and it'll see the far side hemisphere and do the observations unimpeded from any ground-based terrestrial weather phenomena event and being able to monitor it. And in the process, it has a camera system where it'll look at two different spectra, one in the red and one in the UV. And so that beam splitter will be able to differentiate if something was a cosmic ray hit or something was actually an actual impact event. If it was a cosmic ray event, it'll only show up in one of the beam splitting channels. It won't show up in both of them. And that's how we'll be able to quantify that, hey, we did see an impact and then get a better understanding of what the flux rate would be in that process. And again, that'll be on the far side hemisphere. So one of the things that we're going to try and reduce down is that observation bias. Remember, I mentioned terrestrial weather, but that was just one aspect of it. Remember how I said that your observations are based only on the side where it's not lit. So that's the dark side. So you could see these limb biases that are occurring in the process. And likewise, we also see a tapering off of the at the higher latitudes, the polar regions. Is that an observation bias as well? How do we differentiate that? Because we really need to understand how the lunar meteorites resurface or overturn, or some like to use the term garden, but to overturn the lunar surface. And what is that? What's that risk look like? And can we characterize that? So I won't go into too much detail because I know we're getting toward the end, but I do want to show that we do have some good meteorite estimates, uh, but we do have some gap areas for the moon, both in the high energy range and the low energy range. You could see kind of our wide error bars based on some of our ground-based observation, and we're hoping to narrow that down a lot more with Lumio in the future. So I mentioned meteorites. I mentioned ejecta from the meteorites. But what about those micrometeorites, these impactites? I mentioned tektites before, but what about micrometeorites and these glass spherules? How are they formed? Well, we understand they were formed by meteorites, but what about the micro ones? Well, the micrometeorites, we see evidence in what's called agglutinates, and agglutinates have been found all around the surface in the different landing sites, both with Apollo and the Luna missions in the 1970s that the Soviet Union flew there and had sample return brought back. And we believe, based on the current models in geochemistry and the geology, that when a micrometeorite hits the surface, it causes a small vaporization of the silica to form this impact glass. Well, how do these micrometeorites hitting an astronaut or hitting a lunar surface, how are they going to hold up in that process? So that's one of the things we're trying to understand is how often agglutinates hit the surface of the moon. Because remember, we have a great filtering mechanism here on the Earth. We have a stratified atmosphere, but on the moon it doesn't. And that's one of the areas of active research that we're looking at for agglutinates. So this is from earlier test data from the conclusions. We did see that lunar simulant material effectively blocked no more than 2.5 centimeters for high impact velocities that were at the 2 to 300 um, kinetic energy levels. Remember, I mentioned that ballistics were down below 100. These were up to 2 to 300 for what we were observing, and they were able to stop that pretty effectively. And the idea is lunar regolith would be used for habitats, possibly 1 meter for the radiation shielding. And so while we didn't have 1 meter of lunar regolith, we did have about 18 inches of lunar regolith, and it was able to stop it within 2.5 centimeters. And then even less with the lunar regolith simulant using a proprietary epoxy at that time for maybe reinforced structures. So, and then we used some, I don't have it here due to time, but we did do some similar Whipple shielding testing. While it didn't stop all of it, it certainly degraded the velocities and stopped a number of the particles. And so they do show promise. But again, you're doing trade-offs. The higher material, the higher grade materials you use, that's weight coming there. So we were looking at lower grade materials to see if we could stop that type of hypervelocity testing. And obviously, we need to do further testing on different type of materials. Now that we're further along in the Artemis missions, we're hoping that we could get from the Disney report, that's DSNE, not the mouse, but the Disney report is what NASA puts out. It's an engineering study of if you're going to do build a lander, build a rocket that's going to a planetary body, here is the extreme environment you're going to be dealing with, and therefore here's materials that you should use for that. And so understanding those future materials could help in those future Disney reports in that layered shielding or in situ resource utilization shielding that we could use for the future. So that's what we're working on armor. We're going to continue doing some testing. As I told Jared earlier, we hope to finish up some residual testing in the future this year. We'll see to understand the limits of the capabilities of some of the materials. And again, that Lumio mission, we hope to launch in 2028 for our 2029 mission to understand that meteoroid flux rate more fully. And since the research ended at North Dakota in terms of funding, the Mariner Space Institute, which just stood up in January, we've picked up armor and we'll be continuing this Artemis-related habitat and hazard mitigation efforts in the future, which we look forward to. So, sort of a tease from the Mariner Space Institute, but armor will continue on as it has been for the last couple of years. And with that, I believe that's my last slide. Yep. And I will stop sharing and switch it back over to Jared.
Awesome. Thank you for the presentation, Jacob. This is really cool stuff. And like I told you, a topic that we hadn't really explored here at this webinar series. So I appreciate you. Well, and it's actually underexplored in the community in general. So thank you for taking the time to lend your expertise and inform us all on this critical hazard that we need to address as we work towards lunar permanence. But anyway, enough from me. We do have one in the Q&A. Caitlin Ahrens, hi Caitlin, says, would your risk objective also account for timing risks? That is, mobility distance risks of rover slash astronauts from point A to point B, or even timing of the moon through meteor showers, which has a noted increase of impact flashes. Great question.
That's a great question. There's a bit to unpack there in the process, so forgive me if I skip one part. Let me lead with the meteoroid stream because I wanted to talk about it, but I didn't have the time. So it has been postulated that there is an increase in lunar impact flashes during meteor storms. Um, Having said that, the data doesn't reflect that. Um, it does seem um, it does seem that it tends to be uniform, um, but it's strongly believed by the geologists and astronomers on the teams that there's a strong observation bias because of that sunlit side, and uh, that's preventing us from seeing that. And certainly, we also recognize that there is probably a lower limit threshold on the telescopic observations that are probably also not picking that up. But at least at the medium range or higher range, they're about uniform from what we can tell. That could very well change, and I do expect it to change in the future in the process. But that was interesting. You would have thought, even with our limited observation bias, there should be kind of a standout in that process. Um, Having said that, I would imagine if I was an astronaut, I would be concerned during a meteoroid storm. The problem is if you look on, I was pulling up the app earlier, but I don't know if I need to do an update or not. But there's a couple apps out there that have meteoroid showers that occur, and if you notice, they're every 3 days in a lot of cases. So, you're sending astronauts into shelter on a fairly regular basis. So, I think part of it is we would need to not only understand and that's what we're hoping to do with Lumio. We're hoping to see which meteor streams are probably the most hazardous, where you probably do need a shelter. On the other ones, they're probably with the background noise, so it's probably no different than what we have to do. So that's probably the first answer to your question is we need to quantify the risk of meteoroid storms, showers versus normal background meteoroid flux. And we hope to do that with Lumio. um, in fact, that reminds me of a good paper topic, putting that in for that meteoroid stream. So I'm going to write that down. So thank you, Caitlin, for that. Um, but so we need to understand that part. And then the other question I want to make, or other aspect, I think, was in rovers. So that's a good point. That's actually a strong point. I have, and that's why I've been eyeballing or bird dogging the lunar rover awards that NASA has been putting out, because I'm very curious. Most of them have talked about we're going to have good traction and good wheels and make sure that we can traverse, and we want astronauts to get in and out very quickly. Well, that's great that you're agile, but I don't know if that's safe, to be honest. Would you want something that's hardened or protected? Granted, if you got to move fast and you want to get back to base to get in a shelter, that might be useful. Um, one of the comments that was made was, as an astronaut, one of the Apollo ones, they said, yeah, we don't so much care if there were holes in the lunar rover, just as long as the thing could operate, which I thought was an interesting observation. Obviously you don't want to be there when it's hit, but yeah, you could probably continue to drive that rover because if I recall on those rovers, really the mechanism is that motor in the front. So if everything else got punctured, you could probably still drive it around in terms of mobility from a rover standpoint. I think as an astronaut, with an EVA suit, talking to Dr. Pablo De Leon, who does a lot of spacesuit work, both for NASA and other groups down in Florida. He's always said if there was a direct strike on an EVA suit, no matter how much protection you're doing, it's probably a bad day when that occurs. Hopefully, I still think like a direct strike is you're 6 times more likely, if I recall the statistics, of being struck by lightning here on Earth than being directly struck by a meteorite on the surface of the moon. But those are big strikes. Those don't account for micrometeorites and don't account for ejecta. And that's the part that we're trying to understand. Um, and I'm not sure I have a good answer for that mobility for an astronaut that's out there. I'm not sure anybody does just yet. Um, and then I think there was another part of the question. I'm trying to remember what it is. Did I get all of it, Caitlin, or was there something I'm missing? I remember the meteoroid storms. I remember the mobility in terms of timing for the operational risk. But if there was something else, go ahead and mention it again in the chat.
I th Well, I'll give Caitlin a sec to type if needed. But the initial question, from my understanding, you hit every single point and eloquently so. Thank you for that. Um, Caitlin says, yes, I think you got it. Awesome. So I don't see any other in the Q&A right now. So I'm going to jump in with a question I had.
Sure.
What, I guess, this is kind of a tricky part, and it's a political question in a way with probably no good answer. But we see these hazards,
My
and
favorite
like
kind.
you've met, there's been a lot of work done, like you said, on the radiation and thermal shielding and insulation. This impact hazard is obviously significant to literal human life as well as health and well health of our hardware and infrastructure that we eventually develop. But I personally haven't seen it being pushed a lot that this is a problem by programs within space agencies per se. Now, maybe that's just my own observation bias here, but if it's not, what do you think are next steps to make it clear that this is a problem for lunar permanence? And what are your proposed solutions to get some of this shielding sooner than later?
Yeah, that's a great question. I don't think it was too political at all. I think it was great. Um, yeah, so a couple things in the process. We're still working on a few publications that need to come out, and I think that will start to drive some of those questions in the process. We have a draft in, and I know we're doing revisions with that, but there's going to be some subsequent papers to that. The other part is the Disney report that I mentioned, DSNE. That is probably where it needs to go. It needs to go in there. And the NASA Marshall team, who's responsible, and forgive me, let me take a step back because I know not everybody knows this. NASA's has different NASA centers, and each center is responsible for different aspects. NASA Johnson Space Center is responsible for pre-Artemis and up to Artemis 3 mission planning. NASA Marshall Space Flight Center is responsible for Artemis 4 and beyond infrastructure. So that's kind of why there's that maybe not that focus. And right now, if you talk to the NASA Marshall spaceflight team that's involved in doing Artemis 4 planning, they're telling me it's important, but we're still trying to figure out how to land astronauts safely. You know, I mean, they're literally in that still stuck area. They right now, and this one is going to get into my follow-on question of what you asked, Jared. So it's not meant as a tangent to avoid. I'm actually going to bring this full circle. And that is right now, NASA Marshall is struggling with how do you develop a safe landing zone? So when you think about it, the Apollo lunar excursion module was one nozzle. It came down and there was no infrastructure, right? Everything was self-contained in that Apollo lander in that process. And when they blasted off, they just blasted from the top with a single nozzle. All the plans right now are for multiple nozzled spacecraft to land and then take off. Well, that is really detrimental. That plume exhaust, that plume ejecta is extremely detrimental to nearby hardware. And I'll give you a good example. The Apollo 12 mission landed near Surveyor 3, I think it was Surveyor 3, if I recall correctly. And one of the experiments of Surveyor 3 was, hey, we want to see how much ejecta is coming off the lunar surface. Well, the problem was they actually had plume ejecta interfering with the micrometeorite ejecta. And that was what, 1 mile away? So is the plan, and this is what NASA's Marshall's struggling with, is are we supposed to put a landing zone several miles away from habitats? That's not practical. They're trying to figure out a safe landing zone on the plume ejecta. Now, I think that's one area that NASA at both agencies are concerned about, and that is what does that plume ejecta look like? On a couple of the CLIPS missions, they're actually studying plume ejecta and what that hazard is. And I think that'll dovetail into the meteorite ejecta that we're trying to do.
Well put, well put, and I do agree. And yes, you are right. I was not giving enough credit where credit is due. The survey, I believe, Surveyor 3 was part of my dissertation.
I love
It
that
was
mission.
that's great. It was a couple hundred meters from the Apollo landing zone, the
Okay.
Apollo 12 landing zone, but it was also on some lower topography. Surveyor 3 actually landed in a crater, and Apollo 12 landed outside that crater. So it wasn't just lateral transport. It would have had to go vertically down to
Mhm.
get that to actually affect Surveyor 3. And even given those topographical differences, and with how the ejecta are launched from under the Apollo 12 LEM, it still got sandblasted, like you said. So huge, yes. But anyways, I digress. Thank you
Oh, I love that
for
mission.
it's one of my favorites. They all are, but anyway, yes. Thank you very much for your answer on that. Oh, I I forgot to mention at the beginning of this, sorry folks, that these talks are actually recorded and put on YouTube. Um, I will be uploading this within a couple days after from now. So I'm going to put a link in the chat for all of us to be able to grab. And if anyone doesn't get this, it's in all the announcements, and I can send it separately if anyone reaches out to me. Here's a link to the Space Resources, to the AIAA Space Resources Technical Committee, which I'm the Education and Outreach Chair of, where we upload all of our webinar videos. I'm also going to go grab, while I'm talking here, I'm going to try to multitask, um, to grab the link where some of the slides are uploaded. Jacob, well, I'm actually not very good at multitasking usually. Do you have any parting comments while I dig up this link?
No worries, no worries. I just want to say thanks everyone for the opportunity to do this. I think what AIAA is doing is important for these type of uh, not only STEM education lectures, but also for us researchers out there to ponder questions and ponder the things that you're concerned about, not only for Artemis, but also beyond, just in terms of space resources. You know, I often tell folks this, we might be the very last generation to look at the moon uh, and not see lights and not see some sort of infrastructure there, which is both fascinating and I don't even know what the right word is. It's fascinating and both terrifying, maybe at the same time, that we're about to go through this monumental change. But also, like the early explorers, there's risk associated with it, right? And so, having dedicated scientists looking at this, like Jared, myself, and hundreds, if not thousands of others, is important. I do remember talking to one of the engineers, Fred Peters, who worked on the Apollo program. He said, you know, our goal was to get to the moon in the end of the decade for Kennedy's goal that we had there. And it wasn't until the later J missions, Apollo 15 through 17, before they really started ramping up the science part. And I have to put my hats off to the Artemis team. They really have reached out to the scientific community ahead of time
Mhm.
to start looking for, hey, what problem sets, what things do we need to understand? Because they realize it's not just flags and footprints this time. This is a long-term stay. And how do you do that? Think of like Antarctica. When you send teams down there for National Science Foundation, there's a lot of planning there. And that's here on Earth. And we understand Earth pretty well, but there's still dedicated planning. We got to do that same dedicated planning in terms of rigor, risk assessment, and forward thinking in that process. And I'm just happy to be a very, very small part of it, but an important part. And for those who don't know, uh, a shout out to Jared and his team who provided that lunar regolith simulant. That was really clutch at the timing because all of a sudden we had an open window for the hypervelocity impact lab, and that team came through. So I'm going to do a shameless plug for SRT that they come through when you need it. So that's it. And Jared did not pay me to say that. I just wanted to express my gratitude because I realized I never did. So thank you.
Oh, of course. And that was even before we spun off. So thanks to the UCF team as well. So okay, so everybody, with the one-ish minute we have left, I did punch in the link to the slide repository. You do need to log in to AIAA through this, but you do not need to be a member or pay dues for AIAA to access this. You do need an account, but all that takes is being willing to give your email and password. So if you can't access it for any reason, please let me know. There's also the YouTube link just above that in the chat. If none of this is working, please reach out to me and I will get it for you. Um, in the meantime, that's our time. So again, Jacob, thank you so very much for lending your expertise to this webinar series. I learned a lot and I hope others did too. And stay tuned for the announcement early next month for next month's webinar, everybody. But in the meantime, Jacob, thank you again. And I hope you all have an excellent day. To the moon.
Thank you. Thank you so much. Thanks, everybody.
Bye, everyone.